Assalamualaikum, good morning, good afternoon, good evening. So, the previous video, you learned about properties of beam sections, including centroids and center of gravity. Now we're going to learn about moment of inertia. So, yeah, previously you found out this. Let's continue. CO4 will fall under this lecture. So, lecture outcomes, moment of inertia, and the parallel axis theorem. Now, what's that? Don't worry, we'll take a look at that later. So if you want to cross a river, which bridge would you choose? The engineer would choose number 1, but the practical person would choose number 2, because walking across number 2 is quite easier compared to walking across number 1. But from an engineer's point of view, number 1 is much more stable. As you can see here, number 1 barely bends when force is applied. Number 2 is quite easy to bend. So the farther away material is from this axis of bending, the harder it is to bend. So resistance of bending depends on the shape of the cross section. This resistance to bending is called moment of inertia. This has a high moment of inertia. This has a low moment of inertia. Now, how do we think about this? So imagine this man with a weight here. As he extends the moment arm, or as the moment arm extends, he's not extending it. It becomes more difficult to hold the weight because there is a higher moment applied to the man. And objects with a greater mass have more inertia. So a bigger ball takes more force or more effort to move because it has more inertia. Now we'll take this concept of moment here and the concept of inertia here, and let's combine them together. So it takes a higher moment to rotate or to bend something with a higher inertia. So that's how we think about moment of inertia. So there's something with a high moment of inertia, you need more force to bend it, to rotate it. It is actually rotating about this axis, okay? So consider a simple blob. The moment of inertia for the small area dA here is y squared times dA. It's just the distance times with dA, but the distance squared times with dA, and same with the other one. diy is x squared dA. Now notice, same as before, same as the Q, the first moment of area, y and x are exchanged. All right. So let's dive into this further. So the moment of inertia for the whole blob is, we have two of them because they have two axes. One is for Ix, which is the moment of inertia with respect to the x-axis, which is why we call it Ix, is the integral of y squared times dA. Same goes with Iy, is the integral of x squared dA, to get the moment of inertia with respect to the y-axis. So the moment of inertia is always with respect to the centroidal axis of the cross section. Now what does that mean? In this case, it's y squared with respect to this axis, but this is just for theoretical, for your theoretical understanding. When we go into the real nuts and grits of it, it's always with respect to the centroidal axis, which means this is the centroid, so this will be the x-axis and this will be the y-axis. So when we use this formula here, Ix equals the integral of y squared dA, this I will be the I of this rectangle, but the axis will be this axis. You get it? This Iy is the integral of x squared dA. This will be for this rectangle, but it will be for this axis. Alright? When we want to find the moment of inertia for any other axis, then we'll use a different theory, but we'll keep that towards the end. So example number 1, using first principles, right? First principles. Find the moment of inertia with respect to the x-axis and the y-axis. So let's find Ix. Ix is the integral of y squared dA. We draw a small area. Which direction to choose? Same as before. The direction of dA follows the same direction of the axis that we are trying to find. So we're trying to find Ix. We need to find, this is the x-axis, so we need to find, draw a small dA which is horizontal, same as the x-axis. So dA is equal to b times dy. Substitute those in. Now notice these limits. Why is there a negative there? It's because our x-axis is here, which means anything that goes above is positive, anything that goes below is negative, and anything on the axis itself is 0. So that means h over 2 is here, and this is negative h over 2. That's why those axes are like that. So substituting those in and integrating, you will get bh cubed over 12. So try to get that. If you don't, then recheck your calculations. Let's find Iy. So again, you can find it with one single small red area, but I'm teaching you the basic principles. So we'll draw another one, a vertical one. And remember that the direction of this area is the same as the axis we're trying to find. So we're trying to find Iy. So y is here, so y will be like that, so the area will be like that. Substituting it in, remember our limits go from here, which is negative b over 2, up to here, which is b over 2. Oh, and I skipped a bit. You should get hb cubed over 12. It's the same like Ix, but h and b are switched. In Iy, it is h which is cubed, and in Ix it is h which is cubed, and in Iy it is b which is cubed. Okay, so that's done. So moment of inertia, different shapes have different moment of inertia, and they're usually found at the end or sometimes in the beginning of certain textbooks, which of mechanics textbooks or structural analysis textbooks. So you don't really have to define moment of inertia for simple shapes, but you do need to define them if you find very complicated shapes. All right, so that's why we learn the first principles, so that we can define the moment of inertia for any shape that we come across. Okay, what about the hollow cross-sectional areas? If you find a hollow cross-section area, all you do is you find the moment of inertia for the big rectangle and you just subtract the smaller rectangle, just like this. You take the bigger one here, which is this one, you just minus the smaller one, you'll get this one. And remember, for the rectangle, the moment of inertia is like this. They're provided in the textbooks. Do the calculations and you'll get, for this one, it's 171.4 times 10 to the power 6 millimeter to the power of 4. So if we have an axis other than these two centroidal axes, we can still find the moment of inertia about different axes, and we use something called the parallel axis theorem. And this is very important because it's very useful. So the formula is like this. Let's just take x for now. So Ix, which is I for this axis, okay, for another axis, a different axis from the centroidal one, is I for the centroidal one, for the centroidal axis, but you need to plus this. plus this at the end, which is A, the area, times with D, the distance squared. Simple enough. You just find I for this, but then you plus A, the area, times with this distance squared. That's how the formula goes. Okay, same with Y. You just find IY, but for the centroidal axis, plus with ADY squared. The area times dy squared. Alright? Now remember that this one, for a normal rectangle, for a centroidal axis one, it will be BH cubed over 12. And this one will be HB cubed over 12. Okay? So whatever axis you're trying to find, you just take these two and you just plus on this one, the area of this thing times with whatever distance this centroidal axis is to the axis that we are trying to look for squared. Let's try to see how we can do that. In the case when we have a composite shape, you add up the moment of inertia for all components, but remember to use the parallel axis theorem, because for this shape here, number one, the axis is all the way over here, and for this shape number two is also all the way over here, but the centroid for number two is here and the centroid for number one is here, so they are not, this axis right here is not on the centroidal axis, so we need to use the parallel axis theorem for both of these cases. And this is the formula right here. The total I is the centroidal axis one, I here, centroidal axis I, plus with the area and the d squared for each of the shapes there. In this case we have two shapes, so the total I will be the centroidal axis I for number one, plus with the area of number one, times with the distance of one from, one squared from the centroidal axis, plus with I to the centroidal axis of number two, plus with the area of 2 times with d2 squared. Oh, and might be a slight problem here. Not this one, sorry. It's going to be this one, these two, sorry. It's going to be this d is the distance from, so this is d1. So let's talk about d1. d1 is the distance from the centroid of d1 to the centroid of the whole body. d2 is the distance from body number 2, shape number 2, to the centroid of the whole body. Okay, let's look at an example. So find the moment of inertia with respect to the centroidal x-axis of the whole cross-section. Find the centroid first. This time, let's use a table. So you draw a table like this, I, B, H, the area, which is B times H, and you have your Y, which is the distance of the centroid to the distance of the middle of number 1 and middle of number 2 to the reference axis here, if I'm not mistaken. Oh no, it's just the distance of this to this one. Ah, yeah, that's correct. Yeah. Okay. All right. So B times H is A. Yi for number 1. Y for number 1. Okay, should be from here all the way here. All right. And for number 2, it should be just this. Okay, there we go. So just use the table, multiply everything and add everything together. You should get Y bar is 60 millimeters. Right. So once we find the centroid, now we can do our calculations. So Notice that the distance of y for this one is from the bottom here, but the one for when we want to use the parallel axis theorem, it's with respect to the centroid, okay? It's not with respect to the bottom here, okay? All right, let's continue. So we have already found y bar. Now let's try to find the total moment of inertia. Again, we use a table. So I, with respect to the centroidal one, which is IIC or IC, we have the D, which is the distance from number 1 to the centroidal axis here, which is written down right here. D1 is this. And then you square it here and you multiply with the area. You get this. Then after you multiply with the area, you get this value. You just add it with this value here, and you get this one, which is the same as you applying the parallel axis theorem for just a single body. So just imagine if number 2 doesn't exist. We want to find the moment of inertia of number 1 with respect to the x-axis of this one, the centroidal x-axis, which is offset from the natural centroid for number 1. You see it's offset a bit, and then we need to use the parallel axis theorem. Okay, so just follow this table and you'll get 27 times 10 to the power of 6 millimeter to the power of 4. Okay, so try to see this diagram, try to do the example. If you have any questions, just send me a message. I'll try to clear that up for you. Now try this. Find the moment of inertia with respect to the centroidal y-axis. Yes, the centroidal y-axis. And the answer you should get is about 69.8, 70 times 10 to the power of 6. Right? Try to do that example. It should be quite straightforward. If you don't get the answer, then send me a message, come and see me. We'll try to clear things up. Don't be pushed around by fears in your mind. Be led by the dreams in your heart. So it's nice to have some dreams or some aspirations, okay? So always aim high. If you don't miss, sometimes you're still high, okay? And if you aim low, you'll hit a lot, but you'll be aiming low all the time. You'll be getting low shots all the time. So try to aim high, and if you miss, then you'll still be high, right? So thanks for watching.